Hello everyone and welcome back. So today I'll be talking about what a derivative is, but more importantly I'll be talking about why the derivative is. That is, why we feel the need to define a completely new branch of mathematics to bring about derivatives and integrals, and what do they really mean. And that is, at least what the derivative means is what I'll be talking about in this video, and why Newton felt the need while the plague was going on in England so many years ago to invent a completely new branch of mathematics. But before I talk about the why, let me just briefly state the formal definition of the derivative. That is, suppose if you have a function f of x, f dash of x is defined to be the limit as, say, suppose an arbitrary variable h. As this arbitrary variable h tends to 0, where we have f of x plus h minus f of x by h. And at first, this definition, if you haven't really seen it before, it really seems quite intimidating and overwhelming, and you don't really understand what all of it is about. But I assure you that by the end of this video, you'll have a pretty good idea of what this whole expression really means. But let's keep this definition aside for the time being. Instead, what I will ask you to consider is a person running a race here. Let's say that we managed to find a function s that tells you the distance that this person will cover in some time t. So suppose this function could be denoted by the letter s, and I give it a bracket over here to indicate the fact that it is a function of time. And we also have a graph for this distance time function. That is, it's a very simple graph. We have an x and y axis over here. This is s, this is t, and we see that the graph is a straight line. So if I were to ask you what is the average speed of this person between, say, time t1 and time t2, you would tell me that the average speed is the total distance covered in this time divided by the time taken. So if I were to say v average, and if I were to say this is suppose s2 and this is suppose s1, you would tell me that the average speed is s2 minus s1 by t2 minus t1. Pretty simple. This is standard way of calculating the average speed in a given interval. But think about what exactly you're doing over here. When you do this calculation, that is s2 minus s1 by t2 minus t1, let's look at this triangle that we found over here and see what exactly we are doing. So clearly s2 minus s1 is nothing but this line over here. That is, it is this side over here. And t2 minus t1 is simply this side. So if I try t2 minus t1. So when you do this, when you find this ratio, what you're doing is effectively finding the tangent of this angle, right? And since this is a right angle triangle, I can also say that tan theta is equal to s2 minus s1 by t2 minus t1. So effectively speaking, whenever we are finding the average speed over any given interval, what we're actually doing is we're finding the tangent of this angle over here. And in our case, this angle theta is also the angle that the line makes with the x-axis, which, as some of you may also know, is called the slope of this particular line. And since it is a line, the slope is constant throughout for all t. That is, if I were to extend this beyond, it would still be a constant slope. So what this means is that since the slope is constant, the value of tan theta is same everywhere. And this means that the person is running with a constant speed. And naturally, since he is running with a constant speed, the average speed must be equal to the constant speed, which is the same throughout. But what if the person is not running with a constant speed? What if I were to draw another graph down over here, and suppose if I were to say this is s dash of t, that is some other function. Okay, well, I should not be using s dash because that is used to denote the derivative. So I'll say suppose s2 of t. So I will draw another graph over here, and in this case I will take a wavy line of this manner. I mean, this is, they saw the person running and they drew the graph in this manner, whoever was observing the person running. And what they found was this is how this distance that he covered varied with time t. In this case, clearly the speed is not the same throughout. You can see that in this time, suppose say in this region over here, he's going pretty fast because he's managed to cover a lot of distance in pretty less time. Whereas in this case, he's lagging a bit. He's covered pretty less distance in a lot more time. So you can see that the person is not running at the same speed throughout. And but you could still calculate the average speed, right? So suppose if I gave you a time t1 over here and time t2 over here, and again if I gave you s2 and s1 over here, you could say, well, I know what s2 and s1 are, I know what t2 and t1 are, then v average over this interval should again just be s2 minus s1 by t2 minus t1. There's no problem. And so this is pretty valid to do. We can still find the average speed. But what if I asked you to find the average speed or the speed that the person is running at this point time t? So I asked you at this particular time t, what the speed of this person is. Would you be able to tell me? And the answer is no. Whereas you would have been able to tell me in this case because the speed is constant throughout, so I would say that the average speed is equal to the speed at this time t, and you could simply say that the speed at this point, suppose at this point over here, is simply s2 minus s1 by t2 minus t1. But in this case, the average speed is not the same throughout. And this is exactly where the idea of a derivative came through. It is used to find the rate of change of some function with respect to a particular variable at any time throughout this particular graph. Or in this context, it can be used to find the speed of the person at any time t and not just the average speed between two intervals. So the question then is, how exactly do we go about doing that? One thing that we could do is run with the same idea of average speed, but we've seen that it's pretty inaccurate, right? I mean, if you were to find, we'll just draw a triangle again over here. S2 minus S1 would be somewhat like this. And as you can see, that is wildly inaccurate. It really doesn't give us the speed at that point. But what if we were to make the interval much smaller? What if instead of having the whole interval t1, t2, what if we could shorten the interval to suppose somewhat like this? What if we could make it even smaller? In this case, it does seem pretty accurate because it begins to resemble what the graph looks at that point. That is, if I were to draw the slope over there, you could say it begins to resemble the graph at that point. And this is exactly that idea of calculus, of derivatives, of integration. We keep making things as small as we can in order to approximate the graph at that point. And so what we actually end up doing, and I'll draw a fresh graph over here, is if I were to draw the graph S again, what actually happens over here is we try and keep, suppose we want to find the speed at this point, say t naught. What we do is we have a variable, say t over here, that we keep on bringing closer and closer to t, so that if I were to say keep on drawing lines over here to indicate the interval, what I will actually do is we'll keep on bringing it closer like this, like this, like this, such that it is almost at t naught but never at actually t naught. And that is basically the limit as of, suppose the function is s, as t tends to t naught. And when we say t tends to t naught, we are basically saying that t gets very close to t naught, but it never actually becomes t naught. It never actually gets to the point of t naught. And so in this context of t becoming very close to t naught, the definition of the derivative really becomes clear. So let me write the definition again, and instead of using s and t, I'll switch to f and x, but the idea is the same. We are still trying to find the average speed or the average rate of change as the interval becomes very small, that is as t tends to t naught or h tends to 0. So let me draw the graph again, and now we have f and we have x over here, and again we have an arbitrary function over here. It really doesn't matter what the shape is, and we want to find the derivative of this point x. So what we will be doing over here is we have some point, suppose say x plus h. This is the other point that we had in the previous case, which we called t. So x plus h is a point and h is a variable quantity. It can be whatever we want, and what we are going to do is we are going to tend h to 0 such that it becomes closer and closer to x. That is, as h tends to 0, clearly x plus h will become x, but it never actually becomes 0. And if we wanted to find the average speed or the average rate of change, what we would do is we would then find the value of the function, that is, we would construct a triangle, right? The value of the function at x plus h and the value of the function at f of x. And then we would construct this triangle over here, as you can see. So clearly the average rate of change or the average speed would be f of x plus h minus f of x, and if I were to divide that by the horizontal, that would be x plus h minus x. So let me write that as well. And we can cut the x, and you begin to see the similarities to the definition that we had earlier. But this alone is not enough, because we haven't specified what exactly is happening to h. This is in general just the average rate of change over x plus h, the interval x and x plus h. So instead what we will do is, to sort of seal the deal, you could say, we will finally write limit as h tends to 0. And this is the derivative basically. So as h is made very small, the value of this function basically begins to resemble the graph at that point. That is, it gives the slope of the tangent line to the function at that particular point, which we call the derivative of the function at x. So let me just state that again. F dash of x, that is the derivative of the function or the rate of change of the function at that particular time. Or if you still like the speed analogy, it is the speed of the man at that particular time. That is equal to f of x plus h minus f of x by h as the whole thing, the limit as the whole thing of that tends to 0, the limit of h as it tends to 0. And this is the derivative basically. Now in the next video I'll be trying to find the derivative of some common function that you see or encounter while doing calculus, that is x raised to n, sin x, tan x, sec x, e to the x and ln of x. And in the video after that I'll be looking at the chain rule. So I hope you've learned something new, and thanks for watching.